Happy International Day of Mathematics to you around the world. The 2025 theme for the International Day of Mathematics is Mathematics, Art, and Creativity. It is our pleasure to welcome you to this webinar. With its title, Mathematics and Creativity in Art and Education, it touches the three missions of UNESCO, namely education, science, and culture. The opening remarks will be given by Mr. Shao Feng, Director of the Division of Science Policy and Basic Science at UNESCO. Mr. Shao Feng.
Thanks, Professor Christina. And dear all professors, artists, and excellencies, and distinguished guests, esteemed educators, researchers, students, and all those who found inspiration in the beauty of mathematics. Happy International Day of Mathematics. It is really a great pleasure to welcome you to the International Day of Mathematics 2025. Today, we come together to celebrate mathematics as a pillar of scientific advancement and as a profound source of the creativity and innovation. Since its proclamation by UNESCO in 2019, this day has served as a reminder of the universal power of mathematics, one that transcends culture, disciplines, and generations. We often think of the mathematics as the language of science, engineering, and technology. It enables us to model climate change, optimize resources, and unlock the potential of artificial intelligence. However, mathematics is also deeply interconnected with art, music, and design. This year, the theme, Mathematics and Creativity in Art and Education, invite us to view mathematics beyond just numbers and formulas, recognizing it as a force that shapes beauty, imagination, and human expression. Mathematics can be found in the symphonies of Bach, the sparrows of seashells, the fractals in nature, and the proportions of the Parthenon. The Fibonacci sequence appears in the branching of trees and the patterns of the sunflowers, while the golden ratio has inspired artists and architects for centuries. Today, digital artists use algorithms to create stunning visual masterpieces, and artificial intelligence models generate music based on mathematical structures. This theme allows us to explore the dynamic ways in which mathematics and creativity fuel each other, leading to new frontier of the discovery. At the heart of this celebration is education. UNESCO is deeply committed to strengthening STEM education, ensuring that mathematics is accessible, engaging, and inclusive for learners worldwide. Mathematics is more than just a subject. It is a way of thinking. It equips individuals with the skills to analyze, innovate, and solve complex challenges. But yet, for too many students, mathematics feels distant or intimidating. By integrating creativity into mathematics education, we can make learning more interactive, visual, and inspiring. This is especially important as we advance the International Decade of Sciences for Sustainable Development from 2024 to 2033. Mathematics is at the core of the sustainable solutions, from the predicting natural disasters to designing energy efficient cities. UNESCO encouraged scientists and researchers worldwide to participate in this initiative by submitting proposals that leverage mathematics to drive innovation and sustainable solutions. Moreover, in this International Year of the Quantum Science and Technology, it is essential to recognize that mathematics underpins quantum mechanics, quantum computing, and emerging quantum innovations. Encourage creative approach in mathematics education will help us cultivate a new generation of thinkers who can bridge logic and imagination to shape a better future. Today, I want to acknowledge those who bring this vision to life, the artists who transform mathematical concept into breathtaking works of art, seeking numbers not only abstract symbols, but as tools for storytelling and beauty. The educators who nurture curiosity in the classroom, making mathematics an exciting journey instead of the obstacle. And the scientists and the researchers who use mathematics to push the boundaries of what it is possible, helping us decode the complexities of the universe. As we engage in today's discussions, let us embrace mathematics not just as a discipline, but as a universal language of discovery and creativity. I look forward for the insight and innovation that will be discussed from today's exchange. Thank you and happy International Day of Mathematics again.
Thank you, Mr. Shaofeng. So the keynote lecturer of this webinar is Ingrid Dobschi, one of the world's most famous mathematicians and a recipient of a L'Oréal UNESCO Award in 2019. Ingrid Dobschi is a specialist of wavelets, a very powerful tool for analyzing images. She is also very passionate with art, and this has led her to work with museums around the world. Today, she will talk of mathematics unlocking art's hidden secrets. Ingrid.
Thank you so much, Christian, and I'm very excited to be here and share this presentation with you. Okay. Well, I work with high-resolution scans of paintings. So digital pictures consist of pixels. You'll see that many times here today, which are small squares. Here they're shown as rectangles, each with a constant gray value. And those are numbered from 0 to 255, 0 for all black and 255 for all white, and with many grays in between. So once you have them in numbers, you can compute with them. So if I take this very tiny little line here in this paint, is this self-portrait by Van Gogh, where I have given numbers below 100 in bold and the others less bold, to remind you that low numbers are dark, I can look at a tiny portion of them and see that many of those pixels have numbers very close to each other. So if I can take that into account by computing for consecutive pairs, their average. And again, they're very similar. I can compute their averages. Now, I've lost information in doing that. The information I've lost is for each pair, the difference between the numbers. You see those here. And at the next averaging, those were the differences. And what you see is that by doing that, I've automatically found the places where there was a big transition. So operating with those numbers, doing computations, tells me about things that are going on in the image. And of course, in real pictures have pixels in the two directions, horizontally and vertically. So operations are done in both directions. And that will tell us that there is information at many different scales. So let me visualize this. I take here these clocks by Van Gogh. If I blur them, which you do by replacing every pixel value by an average of the pixel value itself and its neighbors, then you get a blurrier image. You can then look at the difference between the numbers and interpret that as an image. If you do that, you see this, and I enhance it here. And you see that it gives us very clearly information about the edges, because this way of comparing gives us edges in the image, because that's the transition between sudden dark and sudden transition between dark and white will be changed by a blurring. And so there's different information there. But I can do this over and over again. I'm going to show you only on a tiny little bit of this painting, but I keep repeating that. And you see here that the differences, successive differences, will tell me that things are going on. Now, the color in what you see in the differences is a false color. It's to distinguish the positive from the negative differences, depending in what direction we go. But so you see, I have difference at every scale. And if I look at those differences, there are things that stand out at all scales, like here, because that was an edge in the clog. But there are other places where difference information appears, becomes strong, and then disappears again as we go through scale. So you can use all that to, what I've shown to you is a decomposition into a mathematical tool called features. I've hand-waved a little bit about the technical details, but based on that, on these statistics of when things appear in different scales and at different angles, you can define a distance between patches of paintings and visualize a similarity. And actually what I've shown you was the result of a first question that was asked to me by the Van Gogh Museum when we started working on using image analysis tools on analyzing paintings. And here we made a virtual mobile of which I give you 3 snapshots. The paintings that have red dots in here are paintings that were in their collection, but not by Van Gogh, but had at some point been thought to be by Van Gogh or had influenced Van Gogh. And you see they are more towards the edge of the cloud than most of the paintings. The center is all true Van Goghs. That was just to illustrate, to introduce you to the mathematical tools that I'm using. But those mathematical tools were used in our next project, which was a hidden Van Gogh project. If you had Googled around, I don't know, 15 years ago, a hidden portrait woman, Vincent van Gogh, this portrait that you see here on the cover of Analytical Chemistry would have appeared everywhere in your images file. This was a first study of paintings, which is now a standard tool by infrared reflectographic imaging by fluorescence of elements, done by Joris Dick and Koen Janssen. Joris Dick is both an art historian and a scientist studying materials. So the painting is this painting. It's really horizontal. It's a study of a patch of grass from Van Gogh's Paris period. And it was known that there was a portrait of a woman underneath from his Nuenen period because it shows up in the X-ray. And people were very interested in this particular portrait, even though he painted many others that he did not cover up, because in a letter to his brother in Paris, which he wrote from the Netherlands, he said, I'm trying with a very dark palette with mostly somber colors to nevertheless give an impression of color. And I'm sending you here a painting in which I think I succeeded particularly well. And we have that letter, as we have the whole correspondence between Vincent and Theo van Gogh, but we don't have that painting. Now, this particular painting, the top painting, is a painting from his Paris period. And when in Paris, Van Gogh met the Impressionists, changed his style completely. And so it's not so unlikely that a painting that he valued especially earlier would to him to seem now completely passé, and that he would have covered it like he often did with small paintings that he reused as study, of which he used the canvas again as for studies, because canvas was expensive, would have covered it up and painted something else on top. So, but that's why, because Van Gogh had particularly valued it, people were especially interested in this painting. So what Joris Dick and Koen Janssen did is they took it to a high-energy X-ray source in a hospital where it's used to make short-lived radioactive elements for medical tests. And in the experimental space next to it, to which the beam is directed for physics and other experiments. They put the painting and they analyzed it tiny little bit by tiny little bit. Of course, they had experimented earlier to see that this would not damage the painting, in order to examine it by getting fluorescent images. When high energy X-rays fall on atoms, they ionize certain of the atoms, and then the atom recovers the electron back to get to neutral state. And in some atoms, that happens in 2 steps, in which it first goes to a high energy state and then drops to a lower one. And that last step has a very, very particular energy difference that's characteristic for the atom at which we're looking. And it sends out, in the transition, it sends out a photon of a very particular wavelength. And so by observing what light comes out after the little piece of the painting is struck by an X-ray, is that you can observe the abundance of different elements by the intensity of the wavelengths you get at of the intensity of the light you get at different wavelengths. And so here is the result of looking at every pixel is one experiment, and then the next one, and you see this put together for the element of arsine, which was part of the red that Van Gogh was using. And indeed, you see the lips of the subject stand out. And the other one was for molybdenum, which was part of the Naples yellow he was using, which was the only very bright color he had. And so it stands in, it's a proxy for luminosity. And after I gave a talk about the earlier thing with the Van Gogh Museum, Joris Dick approached me and he said, look, we did this study and we colorized it and we got to this, but maybe you guys can do better. I mean, this colorization is kind of primitive, he says. Maybe you with image analysis can do better. And he very generously shared with me the whole data cube. And the first thing we did was we found that in that data cube, there were some weird things going on, like this kind of zebra thing here. And we said, Joris, what is this? And he says, well, it's very embarrassing. You see, because we had to scan every little pixel by itself. But of course, the beam was not ours all the time. Sometimes it had to go to its day job. And that's when the whole thing had to stop. And of course, the beam was always in one place. It was a sled on which we put the painting that moved for different pixels. And there was a synchrony problem in stopping when it had to stop and starting up again. And that, because the whole scanning was done in zigzag, gave rise to these artifacts. He says, so we don't really know where the breaks happened. We see that they must have happened. So we modeled that with a Poisson process, and we then readjusted and so on. And so the first step we did was doing this nice mathematical process to get to a much better version of what it would have been without the synchrony problem. Then after that, we used all these black spots are caused by the impasto on the top painting that where the X-rays could not penetrate in order to give us information of the painting underneath. So we covered those up, and then we used a technique, a mathematical algorithm that's called in-painting, because it's inspired by what art restorers do when they paint in paint losses by just propagating, because of course you have information before and after. It's brushstroke, so you can infer what it must have been and you can compute that. And so that's what this was. A different algorithm was used for the long impasto strokes. And then finally we needed to change, get extra information around the eye, and we used, like restorers do, the other eye. And we had, and you see how nice and natural that fill-in process has worked. So we then had to go to color. Now, it turned out that we don't have enough different wavelengths to characterize all the colors that Van Gogh used. We don't have anything about any of the earth colors he must have used. We don't have anything about blue. But one of the team members, actually an undergrad student working on this project, had the idea of then looking at other paintings by Van Gogh in the same period. And here are one from the Nuenen period, one that has the least contrast and one that has the most contrast. And if instead of in RGB, as we're looking at them now, you look at them in chromance, luminance, and a third variable. The chromance picture gives you this. And of course, they look very different, but they look very different in where it was black before. Now, because very dark, very dark red or very dark purple or very dark blue all looks the same to us. It looks black. So let's take away the black pieces, and that's what you get. And then we saw that there was a similarity between those paintings that you wouldn't have guessed. And that is characteristic of how Van Gogh painted in that style. And so we could use the similarity to infer information that was missing from our spectral information. And the result was that we got to this version. So using mathematical analysis, image processing tools, we had gone from the version on the left to the version on the right. And Joris Dick was very happy that he consulted mathematicians to talk about this. So we have done many other projects, and you probably can find talks by myself on YouTube that talk about them. But for now, I'll stop here because I want to give room to everybody else who's going to tell you about mathematics and art.
Well, Ingrid, many thanks for a fascinating talk. So we have a number of short presentations by mathematicians and artists who put together mathematics and art. So the first presenter will be Carlene Pilar Arceo, Professor of Applied Mathematics at the University of the Philippines, Diliman. She will show us how in her university she introduces art and creativity inside a math course. So she sent us the video because she was not sure if her connection would be reliable. Bashak, you can show the video.
Colleagues, students, and friends, a happy International Day of Math to all of us. I'm delighted to spend some minutes with you discussing math and creativity in art and education. I'm Carlene Arceo. Friends call me Kayan, and I teach at the Institute of Mathematics, University of the Philippines, Diliman. It is a flagship campus, and it is home to more than 30,000 students, all of whom take up the Common General Education curriculum. Within the College of Science, our institute offers the GE course entitled Mathematics, Culture, and Society. It is described as an appreciation course on the beauty and power of mathematics and its relationship with culture and society. I will dare claim that the power part is already appreciated by many. So, I will focus on the beauty part of the course description. Among the course learning outcomes, I choose two for this afternoon. First is explaining the nature of math as an intellectual and creative discipline, and second is producing creative work inspired by math ideas. Much of the semester is taken up by numeration and geometry. In class, we employ the constructive approach. I explain, I narrate and describe, I show examples. The students react, speak up, discuss, argue, draw, justify, and so on. That's how math and art are the same, right? They are mediums of expression. For modern geometry, we recall the strictness of Euclidean geom, the fifth postulate, the rules on parallel lines, and then together we muse. What if parallel lines could actually meet? What if there were only a finite number of points and lines? And what if most rules are let go of, and only a few remain, like keeping connections? Students are very good at playing that game. What if? Why not? We share stories about Bolyai, Lobachevsky, Gauss, and Riemann. We look at the works of Fano, Papus, Desargues, and Conway. We try answering the questions of Euler and Minkowski. All this while keeping Euclidean geometry as a reference point, as the cause for all the musings. We also talk about numeration systems and how the Hindu-Arabic one emerged as a universal system of choice, the one we all use now. To appreciate what the Hindu-Arabic system may have gone through, students every semester create their own numeration systems. They evaluate each other's works and then choose which one would be the class's universal system. This opens up their sense of culture, community, and intuition and inclusion in communication. Another much enjoyed group activity is the creation of tessellations. Here are some outputs. And the happy faces of their creators. Isn't it wonderful that students look like this in a math class and even ask for more math to do? Feedback has revealed that more than the computations that they had to learn in skills classes, the group activities spurred their critical thinking, creativity, resourcefulness, courage and confidence, collaboration. There's a sense of shared purpose and that problem solving is a group effort. Finally, there are also the individual submissions at the end of the term to that question. So let me wrap up my presentation with some quotes from the students themselves. Math has provided human civilization with so many potent instruments for creativity, science, and practical needs. Math is a journey motivated by curiosity and awe that demands originality and bravery. It involves experimenting, asking questions, collaborating, searching for patterns, breaking out of old paradigms, and arguing persuasively. Math also teaches us to be liberated from the shackles of old ideas and to strive for truth and progress. It is a state of revolutionary zeal. Math is complicated with a complexity that makes it interesting, which is why I compared it to art, a remarkable product of human ingenuity, a pure exhibit of evolution and the metamorphosis of consciousness. Both the arts and mathematics are representative of feeling and experience. They are both arguably entirely human. Math is one of the greatest accomplishments of mankind, and in an ironic yet beautiful way, it is art. And don't we all agree? So, there. I hope you enjoyed my short presentation. Thank you for listening to me and my students.
Thank you, Carolyn, for showing us how we can put art in our math education. So our next presenter is Jacinto Eloy Puig Portal, Professor of Mathematics Education at the Universidades de los Andes in Colombia. He's interested in mathematical art, and this leads him to lead educational projects around this matter. Jacinto.
Bonjour, représentants de l'UNESCO, collègues et à tous. Pour ma présentation, j'ai créé une vidéo commentée par mon avatar.
I am an avatar of Professor Jacinto Puig, graduated in mathematics from the Faculty of Mathematics and Computing of the University of Havana. From the Universidad de los Andes in the city of Bogotá, capital of Colombia, country of beauty, I cordially greet you. Professor has studied the work of M.C. Escher for more than 25 years and considers that this work is a powerful resource for the development of creative potential because it is on the border of art and mathematical science. In this presentation, we will show you model works made by students of the Escher Geometry and Art course, inspired by mathematical concepts and wood engravings by the great artist from the Netherlands. Escher's last engraving was a cyclic rosette of 3 petals. Snakes. Here we show the students' use of symmetry to create a composition of friezes, rosettes, and wallpaper. A central topic of the course is the creation of mosaics in the style of Escher, with various sources of inspiration. The variety of works shows the development of the creative potential of students. This mosaic is one of my favorites, due to its simplicity and symbolism. It represents the most dramatic scene of the tragedy Romeo and Juliet. The cold colors on Juliet give the appearance of death, but there is a heart on her cheek. Romeo cries inconsolably. Other topics covered in the course include Droste effect, spherical distortions, hyperbolic geometry, art of the impossible, origami, fractal art. We have built a replica of the compass point sculpture with the authorization of its author, George W. Hart. Part of the process on the next slide. On the occasion of the 50th anniversary of the mathematics program at the Universidad de los Andes, a large retrospective exhibition was held. I am infinitely grateful to UNESCO for this opportunity to present our work at this important event. Finally, we will present children's work from the STEM plus Art project of the Social Mission Foundation, which includes designs with artificial intelligence.
I'm Dara, the smallest of the foundation. The teacher taught me how to draw with the mouse. I must be very careful. Now I make a sketch. I have to make several by hand before the one I make with the mouse. We know that. Leonardo da Vinci made many sketches and worked for many years at La Mona Lisa. I am the avatar of Dara. Before making a design, we study the symmetries. We know that there are 7 types of friezes, 17 types of wallpaper, and 2 types of rosettes, dihedral and cyclic. An advanced task is designing a mat. Now we will show you some of our designs. Stockings, pajamas, and Christmas cards have been made with our designs. Our dream is to create a children's museum of digital mathematical designs in the city of Bogota. We need many sponsors.
Thank you, Jacinto, for adding to the many ways in which we can bring mathematics and art together in the classroom. We now continue with our second series of short presentation by artists, mathematicians, and educators. Our next presenter is Tara Taylor, professor of mathematics at St. Francis Xavier University in Canada. In parallel to her mathematical research on geometry and fractals, she is involved in an interdisciplinary research program focusing on the interconnectedness of mathematics, art, and education. Welcome, Tara.
Thank you. Just trying to get it set up. Thank you. Thank you to the organizers and the panelists. Especially that last video was beautiful. Wow. It's hard to follow that. So I want to acknowledge that I'm a settler in Antigonish, Nova Scotia, Canada, which is in Mi'kma'ki, the ancestral and unceded territory of the Mi'kmaq people. So I teach undergraduate math courses at a small university in Canada. My research is in fractals, topology, connections between math and art, math education. I do a lot of math outreach to schools and communities. These photos are just from my office. You can see I've got lots of fun things in my office. So my goal for today is just to celebrate the beauty of mathematics. I will share examples of how play is integrated into my research and teaching. The picture here is a drawing by a student. My geometry class last term did an art exhibit, and the theme was tilings. This was one of our favorites. So the importance of play. There's a wonderful book by Frances Su called Mathematics for Human Flourishing, and it has a chapter on play. That's what doing math looks like. You play. And it's important. It's relevant for our survival as a species. There was an article in the National Geographic recently about it. So my story starts with the golden ratio, which is very well known throughout math and arts. And why the golden ratio? So when I was a PhD student at Dalhousie, my work was in computational topology and fractal trees, and I tutored a sculptor. He wanted to learn more about math. He was the one who taught me about the golden ratio. And it showed up in these 4 beautiful trees with angles 60, 108, 120, and 144. And when I would get frustrated with my real work, I would play with the golden fractal trees. And that's where my interest in the creative side of math really took off. After my PhD, I needed to expand my work, and I looked at the Sierpinski gasket, another well-known fractal. It scales by, there are 3 smaller versions that scale down by 2. Here's a diagram showing the iterated function system for the Sierpinski gasket. There's a whole class of fractals called the Sierpinski relatives, which have the same scaling, but different topology, and that's why they were really useful for me to look at. And to do them, we need to do the symmetries of the square. So I also teach many modern algebra classes, and I love to use color to help students play with elements of a group. So here's just a picture of the binary operation table, the group table for the symmetries of the square, and the color really helps students see the structure. Here's what the subgroups look like. You can see that how the rotations are different from other subgroups of size 4. And here's an example of the IFS showing a Sierpinski relative that involves the scaling down by a factor of 2, but also possibly a symmetry of the square. So there are 512 different ways we can put the symmetries of the square together, but there's only 232 distinct relatives. Here are 8 symmetric ones. And of course, when I would get frustrated with my serious work, I would play with these and make pictures and take a break from the hard stuff. Here's some freezes. So I started looking at other classes just again when I would get frustrated. These ones have triangle convex hulls, just like the Sierpinski gasket does. And I would use them to visualize different subgroups of the symmetries of the square. So here are the rotations. I think of them as pinwheels. Here are butterflies. A few years ago, I asked myself, what is a golden Sierpinski spiral? I like to play with things and connect them. This was my first attempt just putting the Sierpinski gasket in a Fibonacci spiral, and it wasn't very satisfying. So I looked at a variation of the Sierpinski one that uses the golden ratio, so it's called the golden gasket, and I put it into golden rectangles, and I liked these better. Another variation of the Sierpinski gasket is something called the Kepler gasket, which uses the Kepler triangle, another triangle that scales with the golden ratio. And I use those to do variations of something called the spiral of Theodorus. More recent work involves color, again, going back to the color because it's always fun to do that with students. I associated a color with each address of the iteration function system maps and played with those. But I wanted to also talk a little bit quickly, I know time's limited, about just hands-on activities that I do with students. So my students built a water demo to demonstrate Pythagoras' theorem. I teach modern geometry, so I really want my students to understand non-Euclidean geometries. Just more hands-on activities to understand topology. Here's a quilt that was, or a crocheted quilt that was made by students to for the modern geometry class on tilings. There's permutations, a drawing of a nautilus shell. Some students did something called fracking or flacking and in our math library. So why play? It deepens our conceptual understanding. It's a break from the serious work. It fosters the creative associations with math, and it helps us appreciate the beauty. So thank you and happy Pi Day.
Well, thank you, Tara. Our next presenter is Hamid Naderi Yegane from Iran, and he's a student in mathematics at University College London. He is using equations to create artistic works. Hamid.
Hello, everyone. I'm Hamid Naderi Yagane, a mathematical artist and a PhD student at University College London. In this short presentation, I would like to talk about the mathematical method that I use to create artworks. The title of my short presentation is Paintings Created Solely with Mathematical Equations. What does that mean? It means I create paintings solely with mathematical equations. It means that I define digital images with mathematical equations, with mathematical functions in such a way that their definition can be fully expressed in a paragraph. Now, what is a digital image? A digital image is composed of a grid of pixels. Each pixel has a color. Each color can be described by three components: the red component, the green component, and the blue component. Each of these components is represented by a number between 0 and 255. It is called RGB code. Whenever I want to create a mathematical artwork, I try to find a mathematical function that defines the color of each pixel in the image I want to generate. By using a step-by-step process, I try to come up with a scenario to define that mathematical function. Sometimes I'm successful to find that scenario, but sometimes I fail. Now, the strong power of mathematical expressions and basic mathematical functions, such as exponential function and trigonometric functions, enables me to not only to find that function, but also to suggest ways to enhance the beauty of my artwork. Now see a number of the mathematical artworks that I have created with this method. Thank you.
Thanks, Hamid, for sharing with us your new way of painting. Our next presenter is Noa El Katabi, professor of mathematics at Université Mohammed V Agdal, Rabat in Morocco. She's also a painter and running an elementary school. Noa will speak in French, but you have translation if you wish.
Merci Christiane. Je vais présenter moi-même, hein. J'ai mon PDF. Bonjour à tous. Très heureuse d'être parmi vous aujourd'hui. En tant que mathématicienne, artiste peintre et fondatrice d'une école primaire, à travers un dialogue entre mes toiles et mes équations, j'ai l'honneur de partager avec vous aujourd'hui quelques-unes de mes expériences en lien avec la thématique de ce webinaire. Ma première réflexion sur le sujet a eu lieu en 2015 lors d'une exposition. J'ai comparé le peintre devant sa toile vierge au mathématicien qui réfléchit devant sa feuille blanche. Ne se lancent-ils pas tous les deux dans une aventure à la recherche de la beauté et de l'harmonie? Dans cette présentation, je vais vous montrer comment mon art et mes mathématiques s'influencent mutuellement. Et je vais commencer par les maths dans mon art. Si vous observez cette œuvre, je pense honorer la phrase de John Nash qui disait à juste titre: l'artiste et le mathématicien partagent une même quête, celle de l'ordre caché derrière le chaos. Si vous regardez la toile et vous imaginez que chaque coup de pinceau est une trajectoire. Si mon état initial commence dans cette zone, on voit bien que je respecte le nombre d'or. Si je commence là, on voit bien que c'est pas prévisible et c'est le chaos. Donc, à travers la dynamique des mouvements, la fragmentation et l'imprévisibilité des formes, la gestion de la lumière, la diffusion de la couleur, cette toile fait écho en moi à des concepts mathématiques profonds, comme les systèmes dynamiques, les systèmes stochastiques aussi, les équations différentielles, l'équation de diffusion, la théorie du chaos, et bien d'autres concepts. Et maintenant, qu'en est-il de l'art dans mes maths? Alors, sans vouloir contredire Paul Dirac, je dirais que la beauté des mathématiques, la beauté des équations est tout aussi essentielle que leur exactitude. D'ailleurs, les mathématiciens sauront reconnaître la beauté d'une démonstration, d'un raisonnement ou même d'un modèle. Et à ce propos, concevoir un modèle mathématique ou composer une œuvre d'art ont bien des points communs. Ils requièrent créativité, intuition, imagination, sens de l'équilibre, esthétique, expérimentation, etc. Concernant la beauté des équations, je cite ici un bel exemple de modèle fascinant qui est l'attracteur de Lorentz, un modèle qui rejoint par une esthétique insoupçonnée, l'art et les mathématiques. Et quand le hasard s'en mêle, je vais vous raconter une anecdote que j'ai vécue lors de l'accrochage d'un de mes tableaux, qui est ici. L'accrochage a eu lieu lors d'un congrès panafricain, le congrès panafricain des mathématiques en 2017. J'ai découvert sur le turban de ma toile, en fait, j'avais fait des collages avec des journaux que j'avais à la maison. Et il se trouve que j'ai découvert ici un article du Monde sur un mathématicien récemment médaillé Abel, qui était programmé pour la conférence et qui avait annulé à la dernière minute. Donc, par un pur hasard, finalement, il a quand même participé d'une certaine manière à la conférence. Et maintenant, comment se manifeste tout ça dans mon établissement scolaire? À travers des activités pédagogiques variées et appropriées, nos élèves apprennent à penser en termes de modèles et structures, à développer leur créativité, leur raisonnement logique, et surtout à comprendre que les mathématiques sont aussi un outil d'exploration artistique. Je vous donne ici deux types d'activités. Donc, la première activité, c'est réaliser des autoportraits en coupant, en coupant et collant des formes géométriques avec du papier canson en couleur pour créer des visages, comme vous voyez, très expressifs, avec des émotions qui se dégagent. Activité très appréciée par les élèves. Une deuxième activité, c'est participer à des ateliers qui mènent vers les mathématiques grâce à la créativité artistique. Pour conclure, je dirais que l'art et les mathématiques sont deux langages complémentaires avec un esprit commun qui explore ordre et chaos, intuition et rigueur, créativité et structure. Enfin, les mathématiques ne sont pas une science dure, elles sont une forme d'art. Je vous remercie beaucoup.
Un grand merci, Noah. We are now pleased to welcome Manjul Bhargava, Professor of Mathematics at Princeton University. Manjul was awarded the Fields Medal, the highest distinction in mathematics, in 2014. In his childhood, he was inspired both by his mother, mathematician, and by his grandfather teaching him the rhythms of Sanskrit poetry. Manjul.
Thank you so much. Can you hear me all right?
Yeah.
Wonderful. It's a great honor to be with you. What a wonderful hour of art and mathematics. Thank you so much for having me, and thank you very much to the organizers for this beautiful event. So I want to begin by wishing everyone a happy Pi Day, and I also want to wish everyone a happy Holi. I happen to be in India at the moment, and Holi is the day of the new year in many parts of India. It's a day where we splash colors and water on each other to celebrate the arrival of spring. So happy Holi to everybody. As Christian was just saying, tradition of art with mathematics, and many of the origins of some of the deepest theorems in mathematics actually have their origins in the arts, in the history of mathematics in India. Holi is actually a very good example of that. Holi is a day where everybody becomes a work of art because they're covered in the colored powders made from flowers in beautiful patterns. And so everybody walks around as a work of art. And the mathematics that happens today on Holi is that the ancient art of Rangoli, which are patterns that one puts on the footsteps of houses before entering, are made with exquisite mathematical patterns, geometric arrangements to make these welcoming, beautiful works of art when you enter people's homes in order to become works of art yourselves when you then get splashed with colored paints and waters made from flowers. So happy Holi to everybody. Happy Day of Art and Mathematics. Happy Pi Day. I thought I would actually talk a little bit about the origins of one of the most important objects in mathematics that happens to have very artistic origins, namely what are known in many parts of the world as the Fibonacci numbers. But in fact, the Fibonacci numbers originate in art. And I want to tell you a little bit about that. And it really illustrates the fine line between art and mathematics. And it's actually one of the ways I myself got interested in mathematics was through artistic works that I learned from my grandfather. And since I learned about this connection between art and mathematics as a child, it's been a passion of mine as an educator to get more students interested in mathematics, not just through the sciences, but also through the arts. And the reason it happened to me is, as Christian said, much of the mathematics that I learned as a child was through what my grandfather taught me about the rhythms of Sanskrit poetry. So let me tell you a little bit about how Sanskrit poetry works and why so much mathematics was discovered through the medium of Sanskrit poetry. And it's not just Sanskrit, it's many other Indian languages that have this way of constructing poetry. Telugu, Marathi, Malayalam, many Indian languages. So this is how Sanskrit poetry works. It consists of syllables, each of which is either long or short. And something like that is true in many languages where one has a notion of stressed and unstressed for a syllable. For each syllable in poetry is either stressed or unstressed in many languages. But Sanskrit and Indian languages take that a little further. Stressed syllables are actually called long, and unstressed syllables are called short. And the reason for that is that the long syllables are actually pronounced for a longer duration than the short syllables. And in fact, a long syllable lasts exactly twice as long as a short syllable when one pronounces Sanskrit poetry. So you can think of it as saying that a long syllable lasts 2 beats of time and a short syllable lasts 1 beat of time. And you can imagine that once you have that mathematical setup where every time you say a long syllable, it takes 2 beats of time, and anytime you say a short syllable, it takes 1 beat of time, that simple setup immediately starts leading to numerous mathematical questions that the ancient poets considered in great detail. So one of the first questions that naturally arises is, suppose you're a poet and you're composing your last line of your poem. It has 8 beats left, and you need to fill it in with long and short syllables. You have 8 beats, you need to fill it in with long and short syllables, where long takes 2 beats and a short takes 1 beat. How many ways can you fill in those last 8 beats? That's a natural question that would arise if you were a poet. So if a long takes 2 beats and a short takes 1 beat, how many ways can you combine longs and shorts to make 8 beats? Well, you could go long, 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 right? That gives 8 beats. Or you could go short, 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 short. That gives 8 beats. But you could do various things in between. Short, long, long, short, long, long, short, short, long. All of those are various combinations of longs and shorts that gives 8 beats, where a long takes 2 beats and a short takes 1 beat. And the question is, well, how many ways can you fill in those 8 beats with longs and shorts? You could do 4 longs, or you could do 8 shorts, or you could do various things in between. So that's the question. And it turns out that the answer, in general, for n beats, if you have 5 beats, or you have 7 beats, or you have n beats in general, How many ways can you fill in n beats with long syllables and short syllables? And the answer turns out to be a very beautiful mathematical construction written by an ancient poet named Virahanka way back in the year 600. So I'm not sharing any slides, I'm just speaking. I just want you to imagine this. So you have n beats and you want to fill it in shorts. How many ways can you fill it in with longs and shorts? And Virahanka, way back in the year around 600 or 700, wrote in poetry the answer, the mathematical answer to this question of how many ways you can fill in 8 beats with longs and shorts, where a long takes 2 beats and a short takes 1 beat. And in poetry, what he wrote, Virahanka, this linguist, this poet, way back in the year 700, wrote that he wrote the following in poetry: write down the numbers 1 and 2, and then each subsequent number that you write down should be the sum of the previous 2 that you wrote down. And then the nth number that you write down will give you the number of rhythms having n beats. Now, this is quite remarkable because Virahanka was a linguist, not a mathematician. And that's what really illustrates the fine line between art and mathematics. So the numbers that you get by first writing down the numbers 1 and 2, and then each subsequent number that you write down is the sum of the previous 2. You get 1, 2, and then the sum of 1 and 2 is 3, and then the sum of 2 and 3 is 5, and then the sum of 3 and 5 is 8, and the sum of 5 and 8 is 13, the sum of 8 and 13 is 21, and the sum of 13 and 21 is 34, which is the 8th number that you wrote down. And that's why 34 is the number of rhythms having 8 beats. So 34 is the number of rhythms having 8 beats, and the sequence of numbers you may recognize 1, 2, 3, 5, 8, 13, 21, 34 are called the Virahanka numbers. And of course, they're also often called the Fibonacci numbers after the first Western mathematician who wrote about them about 500 years later. But it's really interesting to note that these numbers were first discovered in the context of poetry. And I think that's a really beautiful story, especially for today, the connection between art and mathematics. The way Fibonacci wrote about them is also very interesting. It was in terms of the multiplication of rabbits, but it wasn't a realistic story, the way Fibonacci's was a fantasy story where there's a lot of incestuous mating going on among brothers and sisters, but it leads to the same set of numbers. But in the case of Virahanka, 500 years earlier, it's the answer, the Virahanka Fibonacci numbers come out as the answer to a very natural question in poetry that poets were actually interested in long ago. So these are called, therefore, by linguists, these are called the Virahanka numbers after the first person who ever wrote about these numbers. Virahanka, around the year 700, a linguist who discovered one of the most important mathematical objects in history. There's an entire now journal dedicated to these numbers. The reason artists are still interested in these numbers today in India is because the way Sanskrit poetry works is also reflected in the music of India. And so, for example, I'm a tabla player, and when you play the tabla, there's many times when you're improvising in a certain section of the music where there's this dichotomy between long and short. A long takes 2 beats, a short takes 1 beat, and you may need to fill in 8 beats with an improvisation filling in with longs and shorts. So for example, a long may be the phrase on the tabla, it may be dhati gene, and short may be dhine. So you can combine dhati gene and dhine in various ways to try and fill in different numbers of beats. And before you can do such improvisation, you really need to know the repertoire of ways of filling those sets of beats in, and that is the Virahanka Fibonacci numbers that you need to learn in order to do that. I'll just play a short piece for you that shows that dichotomy between long and short, where the 2 phrases are, as I said, dhati gine and dhine, played by my tabla teacher, the great Ustad Zakir Hussain, who unfortunately passed away just 2 months ago, one of the great musicians of the century in Indian music. And we really miss him. I want to show you the way he used to use mathematics in his improvisations. So what you're going to hear now is just a short piece where there are only two phrases, dhati gine and dhine.
I think we cannot hear.
We cannot
because
hear.
Yes, because you're not sharing the sound. If you want to share your sound.
Can you hear now? No? No?
No.
Oh, I'm so sorry. Okay, I'll stop it then.
Okay, so we will move
I'll
to the.
stop there. Okay.
I think we have to move, Manjul, because
Okay. So I'll just end.
Thank
I'll just end by saying so. Even today, this kind of construction of long and short is used in modern music. It's also used in the tango, in modern dance. So these constructions of the Fibonacci numbers, Virahanka Fibonacci numbers, still come up in modern art, even though they were discovered way back in the year 700. So I'll stop there. And since I'm the last speaker, I just want to thank Christian and Betul for organizing this wonderful event. Thank you to the organizers. And thank you so much to everyone who participated today and for everyone who joined. Thank you very much. Back to you, Christian. Thank you so much.
Okay, Betul Tambay, professor of mathematics at Boket Chizi University. She's the chair of the International Day of Mathematics, so she will say the concluding remarks. Betul.
Hello. I hope Manjula and Ingrid are staying with me as we decided to finish together. I will start by thanking many people, but I have to start by Christiane Rousseau, really. She's one of those great examples of how much difference one person can make, I would say. And Ingrid is one of the persons who knows very well her struggle in International Mathematical Union and all these years. So thank you for having us to come to that point, Christian. And thank you for staying with me for the next few years also that you have accepted. And I also thank the International Mathematical Union and the UNESCO team. And I must also thank the place where some real work is done, and it's called Imaginary. The Imaginary team is amazing, and we have seen lots of artwork that Imaginary has been doing too here. And I urge you to see what Imaginary is. And they have created the International Day of Mathematics logo, and they are keeping the website. So I thank everyone for all this, and it is very exciting for me to see how we all are from all over the world and peacefully having 90 minutes of beautiful work. And many people wrote here many times. I was following the chat, stop war. And I am here in the UNESCO building right now, overseeing Paris and remembering what UNESCO was created for, promoting peace. So, and I saw this on the chat. In these days, which are not very easy, I think we have to remind UNESCO the creation reason. I also think that in this time of technology, we shall need basic mathematical knowledge in our future, and Manjul and Ingrid are very good examples in our field. And in both pure and applied mathematics, we will need research funds. And right now we are too much blurred with investing only on technology and artificial intelligence. And pure mathematics and real mathematics, applied mathematics will be needed, and we should know this because creativity comes from art and mathematics and from human creativity. One word that I liked of Sadek, the repetitions of Sadek, how much concentration we need, repetition we need, patience we need, and group effort we need. So I would like maybe Manjul and Ingrid tell us a little bit how they feel before we end it on time. We've been very good on time, Christian, thank you. So if you have some words with us to keep us. Ingrid?
I have enjoyed this program so much. I have seen so many beautiful things and seen heroes of mine explain stuff, and it's just wonderful. And I do want to add, well, everything you said, every thanks you gave, I second wholeheartedly, and squaring it if possible. But I do want to also emphasize that mathematics, unlike very advanced technology, is something that can be practiced anywhere. And we have seen mathematical talent flourish in anywhere in the world, and people reaching the joy of mathematics anywhere, and examples of really talented individuals under very terrible circumstances reaching the highest level of mathematics. So I would like to encourage everybody who can help, UNESCO, UN, and all the people everywhere in the world, even in difficult circumstances. If they can find joy in mathematics, joy is always wonderful, but mathematics can provide it and can lead you far. So my whole heart with you.
Thank you, Ingrid. And Manjul, do you want to add to, as the young researcher, still young? Manjul, you want to say something?
I just want to go ahead and endorse all the thanks that have been given by you and Ingrid. And
yes, he's cut again. So we say, I think it's very exciting that we are in all continents right now, all together. And I thank everyone again once more. Thank you. Goodbye. See you next year.
Bye-bye.
Okay, so happy International Day to all of you, and bring the joy of mathematics and art in your school or everywhere where you work. So very happy International Day of Mathematics.
Bye-bye.
Bye.
Bye. Thank you.
Thank you.
Thank you. Bye-bye. Thank you.